Right, so we'll start off this week by talking about elasticity, stress, and strain. So far, even when we talked about rotational motion, we assumed that objects were rigid, right? And that simplified the analysis of angular displacement, angular velocity, angular acceleration, because then when we assume that the object is rigid, it covers the same, every point in the object covers the same angular displacement and so on. But in reality, objects are actually deformable. Even the objects that we assume to be rigid, to some extent, they are deformable. And there are many objects that are more deformable than others. And so in this lecture, we will deal with the deformability of objects. An example of a very deformable object is an elastic band or anything that's elastic. Common sense tells us that if you apply a force like stretch the elastic band, then we elongate it and we have sort of this change in length. And common sense also tells us that if we stretch with a bigger, essentially when we stretch, we're applying a force, right? And if we stretch harder, we're applying a bigger force and the elongation that results is bigger. So Robert Hooke formally stated this common observation via what we call the Hooke's law, which says essentially that the elongation delta L is directly proportional to the force that's used to elongate that object. So simply you have this elastic band. If you apply a force, you elongate it, you have this change in length. So this delta L is how much the length of that object changed, how much elongation you have, and they're directly proportional. So meaning the amount of force you apply directly influences the amount of elongation. So if you apply double the force, then the elongation will be doubled. 4 times the force give you 4 times the elongation. And the proportionality constant, K, is called the elasticity constant. It's a property of the material which tells us how easily it is to elongate or deform or stretch a material. So the higher the elasticity constant, the easier it is to deform the object. Right. Okay. So materials that are linear elastic, meaning linear elastic means they follow Hooke's law, where the elongation is directly proportional to the force. They're called Hookean. But objects, even if they are elastic, they are only Hookean over a small range of forces. And in that range, we say that these objects have elastic deformation, meaning over that range, when we stretch the object and then we let go, the object normally goes back to its original undeformed shape. That's when we say that the object has undergone elastic deformation. But we all know that if we keep stretching a rubber band, or we keep it stretched over a long period of time, there comes a point where if you remove the stretching force, the rubber band doesn't go back to its original shape. Right? And in that condition where the object doesn't go back to its original shape, we say that the object has undergone plastic deformation. So the difference between elastic deformation and plastic deformation is essentially just whether the material goes back to its original shape, then we call it elastic deformation. If the object remains deformed, even if we remove the force, then that's plastic deformation. And so all objects sort of manifest this graph of how the elongation depends on the force. We will see here 3 distinct regions if you notice, there is this first region where you have a linear graph. You have a linear relationship between the elongation and the force applied to the object, meaning the object follows the Hooke's law, where the elongation is directly proportional to the force, right? And in that first linear region, we say that the object is elastic. If you keep increasing the force, pulling on the object harder and harder, you'll notice this inflection point. So there's a point where the graph sort of changes, we call this the inflection point, and then you enter the plastic region. So so this second area of the graph is the plastic region, which we've learned in the earlier slide, that even if you remove the force exerted on the object doesn't really return to its original undeformed shape. And then finally, you'll notice that at some point, the graph terminates. And the reason for the termination of the graph is at this point, the object fails or breaks. And we also all know that if we keep pulling on an elastic band or a rubber band and we keep increasing and increasing the force, at some point the elastic band breaks. And so at that point, the object fails or breaks, and that's the point here, which indicates the failure region. So we'll talk about failure or breaking towards the end of this lecture. We'll focus more about the elastic region here. So the amount of force that you apply that will cause the deformation per unit area is what we call stress. Stress, this is the Greek symbol sigma, but we can just use stress, the word stress. Essentially, stress defines the amount of force that you apply over a unit area of the object that causes deformation. Okay. So from definition, so this is definition, stress equals force over area. From definition, the unit of stress is Newton per meter squared. Of course, force as a unit of Newton, area measured in meters squared. And and we've learned that if you stress an object, the object deforms. The corresponding deformation is what we call strain, which we'll talk about later. But in terms of stress, there are three kinds of linear stress. We can classify linear stress as tensile stress, compressive stress, or shear stress. The difference between these, they're all linear stresses, meaning the force is applied over a linear region, and the deformation also occurs along a one dimension, along a line. Okay, for tensile stress, it's defined by stretching forces. Notice the direction for which you apply the force. You're essentially stretching the object. The force is perpendicular to the cross-sectional area, and as a result, the object is stretched. Okay, compressive stress. Well, compression, it's probably like easy to understand. It's when you compress an object. So the force, so notice the direction of the force here. Yeah, you have a squeezing force that will compress the object, shortening the length of that object here. Right, so for both tensile and compressive stress, notice how the force is applied perpendicularly to the cross-sectional area of the object. For shear stress is quite different, because then the force is applied parallel to the surface. And a very good example of shear stress is if you have a book and you sort of apply the force pushing the surface applying a force parallel to the surface. Notice how the book deforms like this, like in the figure here. Right. So the only difference between tensile, compressive, and shear stress, I mean, the difference between tensile and compressive from shear stress is the direction for which the force is applied. Okay. For shear stress, the force is applied parallel to one of the object's surface.
Can't shear stress also be caused by a twisting force as well?
Yes. So shear stress can, yeah. So your twisting force has both a component.
Screw, and then you over tighten it, and the head of the screw breaks off. That would also be considered a shear stress.
Yeah, but the twisting force will have a component that's perpendicular and parallel to your surface. So this is like a more of a complex kind of force. So you'll have to resolve it into shear stress and compressive stress if you're tightening it. Yes. Yeah. We will in the level of this course, we will separate those two though. So we won't consider twisting forces, just simply tensile, compressive, or shear. Shear in, yeah, definition of parallel. Right? Okay, so applying stress force over area to the object results to a deformation. The deformation we characterize as the strain. So strain, this Greek symbol epsilon, okay, which you might encounter if you look at the textbook, but yeah, strain is the proportional deformation that occurs as a result of the stress or force over area applied to the object. So there are different kinds of strains. One example, depending on how the object deforms, right? The object can deform via the elongation of it or via the change in shape or bending of the object. So one example of the strain that is caused is the change in length in the object. So in this case, where the object's length changes, then strain is defined as the change in length over the original length. Okay. If you're applying tensile stress, meaning stretching, tensile means stretching, right? So you're stretching this object here, you're applying this tensile force here, then you'll have a corresponding elongation delta L. Of course, when you are compressing the object like so, then your resulting objects will be smaller compared to your original length, in which case you will measure delta L as how much your object compressed. So delta L can either be how much your object elongated or how much it's compressed, depending on whether you're applying tensile stress or compressive stress. Cool. All right, so let's relate stress and strain via the Hooke's law. So Hooke's law says that the elongation is directly proportional to the force that you apply. We learned that stress is related to the force, stress being force over area, whereas strain is related to the corresponding deformation delta L. You have delta L over L0. So we can rewrite Hooke's law in terms of stress and strain. Then Hooke's law in terms of stress and strain can be written as the strain being directly proportional to the stress, right? The deformation is directly proportional to the amount of stress applied to the object. Instead of using the elasticity constant K, we then use what we call the Young's modulus or elastic modulus. So if you refer to different textbooks or the internet, they either use Young's modulus or elastic modulus. It means the same thing. It's the relationship between stress and strain in stress and strain in the object that's being deformed. Right. Okay, so you can play around with this equation. There are three variables here, the elastic modulus, stress and strain. So you can rearrange that equation whichever way you want, and either expand the definitions for stress and strain to relate the equation to the physical properties of the object and the deformation that occurs. But physically, what's the significance of the elastic or Young's modulus? Physically, the Young's modulus or elastic modulus measures the material's resistance to deformation. Okay? So the higher the elastic modulus is, the more difficult it is to deform the object. So it's more resistant to deformation. Right, so depending on the application that you want, it's the Young's modulus or elastic modulus that you sort of look at. If you want to have more deformation or less deformation, then the elastic modulus of that material tells you, which kind of material to use. In general, materials have similar Young's moduluses in terms of tension and compression, but there are some notable differences. For example, bone has different tension and compression moduli, right? So for tension, it's 16 times 10 to the 9 pascals. For compression, it's 9 times 10 to the 9 pascals. So you looking at these values for the elastic modulus for bone, is it easier to compress or stretch the bone? Yeah. I heard compress, yeah. Elastic modulus tells you how resistant the object is to deformation. Then therefore, when you have a smaller Young's modulus value means it's easier to compress the bone rather than to stretch it. So if you want to use a material as a bungee cord, okay, would the Young's modulus or elastic modulus of a bungee cord have to be larger or smaller than that of an ordinary rope? The concept of the bungee, of course, is that once you jump off, the cord needs to stretch quite significantly to cushion your fall. Otherwise, you'll have this abrupt. Once you reach the bottom of your fall, if the rope doesn't stretch so much, then you have this abrupt change in force that will injure you. So if you wanted to use a rope, should the cord used for bungee have a larger or smaller elastic modulus compared to an ordinary rope? Should have a smaller, right? So then the bungee cord should be able to stretch more than an ordinary rope in order to soften your fall once you reach the end of the rope. Right? Cool. So as I mentioned earlier, the elastic modulus is a property of the material. The question is, how do we determine elastic moduli of different materials? Essentially, you do it experimentally. So here is, for example, an illustration of how tensile testing is done to determine the elastic moduli of this steel. You can pull the most common thing, tensile testing, meaning you apply tensile stress. And so you pull the ends of the steel rod. You have here a laser that measures the elongation or the strain, the corresponding strain as you apply tensile stress at both ends of the rod. And by measuring the corresponding strain for each stress, you are able to plot this graph of the graph I've shown earlier. You're able to plot how much elongation there is for particular tensile force applied on the material. And the Young's modulus is the slope of the elastic region. As we've said, the Young's modulus is the ratio of, the stress over the strain. Okay. And slope is equal to force over elongation. So essentially, by getting the slope of the elastic region in your experiments, you're able to determine the Young's modulus or elastic modulus of the material. Right. Okay. And so, yeah, and so we have tables that give you elastic moduli of different materials. And you can also do this for compression. Instead of applying tensile stress, you apply compressive stress and come up with a similar graph, take the slope of that to get the elastic modulus for compressive stresses. Right. Okay. So let's. So we've learned about those three variables: stress, strain, and elastic modulus, and now let's relate them in terms of this numerical example here. How much does a 2-meter bar extend if it's subjected to a load of 170 newtons tensile stress or tensile force? The bar has a cross-sectional area of 34 millimeters squared, and the material is, the material has an elastic modulus of 20 kilonewtons per millimeter squared. So what we want is how much the length extends, or delta L. It might be useful to write down what we know there. We're given the original length, 2 meters, the cross-sectional area, the elastic modulus, and the force, which is a tensile force, 170 newtons. Right. Of course, you can solve this problem by, using the equations and the substituting and deriving the equation for delta L. Let me solve this equation sequentially first, so it's quite clear. Usually, the easiest way to go about this is you start with what you want to find, delta L. Okay, delta L, the corresponding deformation that comes into the definition for strain. Strain, of course, defined as the deformation over the original shape, in this case, length. All right, we know the original length. It's 2 meters. We don't know the strain. Right? For us to know delta L, we need to know the strain. We have to multiply the strain to the original length L0. We know the original length, but we don't know the strain. So we have to figure out the strain. Strain is defined as force over area. It's but then we know the no, sorry. Okay, so the only other equation where strain comes in is the relationship between elastic modulus, stress, and strain, right? So we know that the elastic modulus is equal to stress over strain. So for us to know the strain, we need to Yes, stress over strain. So we want strain, that's stress over the elastic modulus. So the elastic modulus is given 20 times 10 to the 3 newtons divided per millimeter squared. Okay. But we do not know the stress, right? We don't know the stress. Right. So for us to know the strain, we need to know the stress. Stress is defined as force over area. Well, in fact, the force is given. The force is 170 newtons tensile, and the cross-sectional area is 34 millimeters squared. Right, so I can leave my cross-sectional area in millimeters squared because my elastic modulus is given in millimeters squared. My units are consistent even without conversion. So it's okay not to convert to meters squared as long as you're careful to check consistency of units. Your stress will therefore be 170 over 34, 5 newtons per millimeter squared. Okay. And then you sort of work your way backwards. Once you know your stress, right? Once you know the stress, you will then be able to know the strain. Therefore, strain is equal to stress divided by the elastic modulus. So that's 5 newtons per millimeter squared divided by 20 times 10 to the 3 newtons per millimeter squared. Right, I include the units here so that we can check consistency of units as we go along. So the strain is 205 times 10 to the 4. Okay, strain has no dimension because from definition, it's the change in length over length. The dimensions are the same in the numerator and denominator, canceling each other. And then once you know the strain, you can then find the elongation. So once you know the strain, let me just separate. Therefore, your elongation, which is defined as strain times the original length, will be 205 times 10 to the 4 times the original length, 2 meters. Right. 5 times 10 to the minus 4 meters, or 0.5 millimeters. Right. Cool. All right, any question about the solution here? Okay, so maybe you can try the next example. I'll give you some time to work this out. You have a 1.6 meter long piano wire, steel piano wire, and the elastic modulus of steel is given here, 200 times 10 to the 9 newtons per meter squared. The piano wire can be considered to be cylindrical with a diameter of 0.20 centimeters. How great is the tension in the wire if it stretches 0.25 centimeters when it's tightened? Of course, we learned that tension is a kind of force, right? So essentially, what you're after here is force, and the force is about 983 newtons. So I'll give you some time to work this out, but I'll give the answer to sort of allow you to check your working. About 983 newtons. It can deviate depending on whether you round or not, but if you get something close to this, then That would be reasonable. Okay, so let's look at how to solve this. So we have these three relationships here. Stress being force over air. Stress is defined as force over area. Strain defined as change in length over original length, and elastic modulus is defined as stress over strain. Okay, you sort of start with what you want to find. You want to find the tension, which is the force. Okay, force comes into the definition for stress. Okay, so then force is equal to stress times the area. Remember that area there is the cross-sectional area that we want to consider. The cross-sectional area we can solve. So your cross-sectional area, if you look at a wire, you can consider this to be cylindrical, so that if you cut through the wire, the cross-section of that is a circle, right? And the cross-sectional area of a cylinder will therefore be the area of a circle, pi r squared. The diameter is given, from which the radius would just be half of the diameter. So then your cross-sectional area is pi times 0.1 times 10 to the minus 2 meters squared. Right. So the radius is half the diameter, giving you an area of 3.146 times 10 to the minus 6 meters squared. Meters, I converted to meters squared. So you have this times 10 to the minus 2 that converts the centi, the prefix centi, to meters. Or you can just write it out of 0.001 meters. Yeah. Then we don't know, of course, the stress. We don't know. We have to find out the stress in order for us to find the force. The stress will then come in from the definition of the elastic modulus. So the elastic modulus is defined as stress divided by strain. Therefore, stress will be equal to the elastic modulus times the strain. The elastic modulus is given. It's 200 times 10 to the 9 newtons per meter squared. Okay, but the strain, we don't know that yet. We don't know the strain or how much deformation the string has when it's tightened. But the strain is defined as the change in length over the original length. So we can find the strain change in length. So the problem says that the wire stretches 0.25 centimeters when it's tightened. So that's the amount of stretch, 0.25 times 10 to the minus 2 meters. Okay, so I convert again the centimeters to meters. It's important to convert centimeters to meters because your elastic modulus is given as per meter squared. So your units need to be consistent. So a good way to check consistency of units is to include your units in your calculation. So it's 0.25 times 10 to the minus 2, converting centimeters to meters. Right. Times the it's strain that we want to find. So that's the elongation divided by the original length. Okay. So the original length is 1.6 meters long. So that gives you a strain of 1.5625 times 10 to the minus 3. Right. So once you know the strain, you can then work backwards. So knowing the strain allows you to know the stress. Therefore, the stress, which is equal to the elastic modulus times the strain, okay, will then be 200 times 10 to the 9 newtons per meter squared times the strain 1.5625 times 10 to the minus 3. It gives you a stress of 3.125 times 10 to the 8 newtons per meter squared. And once you know the stress, you work your way backwards again. And once you know the stress, then you can know the force from the definition of stress. So the force is equal to stress times the cross-sectional area. The stress you've calculated was 3.125 times 10 to the 8 newtons per meter squared times the cross-sectional area you've calculated earlier was 3.146 times 10 to the minus 6 meters squared. That gives you a force of 983 newtons. Good. Okay, and the strategy for solving stress and strain problems are very similar, right? So it's really just these three relationships, these three definitions of stress, strain, and elastic modulus that come into play in elasticity, stress, and strain problems. And so if we then, so here we've considered so far tensile stresses, tensile and compressive stresses. If we look at shear stress and shear strain, the definitions are still the same. So shear stress, the only difference is that the force applied is parallel, but it's still, the shear stress is still defined as force per unit area, and the corresponding strain is still change in length delta L over original length L0, except that notice where delta L and L0 comes in shear stress, because in shear stress you don't really elongate or compress the object. Instead, you're changing the shape. You're changing the shape of the object when you're applying shear stress. So the delta L and L0 in the definition for strain should be related to the change in shape of the object, as shown in this diagram here. Okay. The elastic, the shear, the elastic modulus for shear stress is referred to as the shear modulus. Okay. And so instead of using elastic or Young's modulus E, the stress and the strain will then be related via the shear modulus. Okay. So strain is still directly proportional to the stress. The change in shape is still directly proportional to how much shear stress you apply to the object. But instead of the Young's modulus or elastic modulus, we use what we call shear modulus to sort of distinguish the compressive and tensile stress from the shear stress applied on the object. So the significance of the shear modulus characterizes the object's response to bending that will change the object's shape. Okay. But the strategy for solving for example, the shear stress or shear strain of the object is the same strategy that we've used in calculating compressive and tensile stresses and strains in the previous examples, right? Okay, if we then apply the force uniformly, if we apply the force or the stress uniformly throughout the volume of an object, for example, immersing an object in liquid, so that water as liquid, then water exerts force on all the sides or all surfaces of the object. Then you have stress being applied throughout the volume of the object. We then distinguish the amount of stress by calling it bulk stress. Bulk stress being applied to all surfaces of the object, and the corresponding result of bulk stress is to change the volume of the object, because it's like squeezing the object on all sides. So what happens is that the volume of the object changes, and the change in object is characterized by bulk strain. So we use the word bulk to distinguish that the stress being applied is throughout all the surfaces of the object, and therefore the deformation that occurs is a change in volume. Right. So bulk stress and bulk strain, they're still directly related, meaning the bulk stress, the change in volume, is directly proportional to the bulk stress, or how much force is applied through all surfaces of the object. And instead of using elastic modulus, we use the bulk modulus of the material, which is designated by B. So bulk modulus characterizes the object's response to uniform squeezing. The key word there is uniform, meaning the object is squeezed uniformly through all of its surfaces, so that you have a change in volume of the object. So again, the strategy for calculating bulk strain is similar, except that instead of looking at the change in length, it will now be the change in volume, because the corresponding deformation that occurs via bulk strain, via the bulk stress, will be to change the volume of the object. So the bulk strain or volume strain will be the change in volume divided by the original volume. The bulk stress will still be force over area, but just remember that it will be the whole surface area of the object, because force is being applied to the whole surface of the object in order to change its volume. Okay. Right. If we apply force on if we apply bulk stress, or the force on all of the surfaces of the object, there's only one change possible, and that will be to compress the object, make the volume smaller. And so there is this negative sign that we have to take into account when we're calculating the bulk modulus in terms of the change in volume, and that negative sign indicates that any increase in pressure or force per area, and we'll talk more about pressure in the succeeding lectures, but any increase in the force applied through all of the surface area will always decrease the volume. And since the change in volume will always be negative, because you have final volume always less than the initial volume, this negative sign ensures that the bulk modulus will always be positive. Right. But essentially the same strategies for calculating, how much change in volume occurs can be applied as the strategy we used in the two examples for elongation with tensile and compressive stresses. Okay. All right, so the modulus of a material depends on the kind of stress that you apply. And so again, here we have the table for different materials. You have Young's modulus or elastic modulus that tells you how resistant your object is to elongation or tensile and compressive stresses. A shear modulus telling you the resistance of the object to bending, change in shape, and bulk modulus telling you the resistance to changes in volume. And for the last part of the Hooke's law graph that we've seen earlier, when you apply too much stress in an object that it reaches its breaking point, then it breaks or fractures, then we say that it has reached its breaking point. There are several terms referring to this, either failure or fracture. They all refer to the same thing when the object breaks. And so once you reach the breaking point, you have essentially determined the ultimate strength of the material, which tells you how much stress, the maximum stress that the object can withstand before it breaks or fails. And the ultimate stress can be different regarding tensile, compressive, or shear, because we have, as we've seen here, we have different, some materials can have different values for their moduli, their resistance to elongation or bending or change in volume. So some materials easily break, in which case you only need a small amount of stress to reach the failure or breaking point. And the ultimate strength or the maximum stress that objects can withstand, you can also test this experimentally. So you can also say that it's a property of every material. And so there are tables that you can look up that will indicate the ultimate strengths of materials. You can find, for example, in our textbook, table 12.2, summarizing the ultimate strengths of different materials. Okay. Okay, but essentially, the elasticity of materials are all related depending on the stress, the amount of force you apply on an object that accomplishes some kind of deformation characterized by the strain. And we've learned about the different kinds of stresses and the corresponding strains that occur, and the kinds of moduli that characterize properties of materials. So this ends our lecture on elasticity, stress, and strain. In our next lecture, we'll sort of look at a different topic on simple harmonic motion, and this will be on Wednesday. So we don't have class tomorrow because it's holiday, but I'll see you on Wednesday for the lecture.